In this video, we're going to start Chapter 5. Chapter 5 primarily will be looking at triangles, and it's going to be looking even closer into how we solve triangles, and specifically how we solve them when we know certain parts are congruent, and how we can prove congruency in triangles. So first, we have to just start on our basics. We need to be able to classify them by their sides and their angles, and then we have to be able to look at what we call interior and exterior angle measures. So some of these should be familiar. First, we have a scalene triangle. Scalene triangles have no sides that are equal. So if we were going to mark it, we could put 1 tick mark, 2 tick marks, and 3. Notice they're all different, so we know all 3 sides have a different length. Then we have isosceles triangles. Isosceles have 2 sides that are the same length. And so as you can see here, we have 1 tick mark, so we know those sides are exactly the same. And then we have equilaterals where all 3 sides are congruent. So if we mark them, all 3 sides have the same amount of tick marks, so all 3 sides are the same exact length. So when I'm asked to classify by sides, I should be giving one of these answers: scalene, isosceles, or equilateral. Then I can also classify my triangles based on their angle measures. If I have all 3 angle measures inside or acute angles, they don't have to be the same angle, but I have 3 sets of 3 acute angles, less than 90 degrees, then it's just an acute triangle. The rest of them are based, the other 2 are based on just one angle. Okay, so an acute triangle, all 3 are going to be acute. In a right triangle, I have 1 right angle. Okay, if I have 1 right angle, it's a right triangle. My obtuse triangle, I have 1 obtuse angle, that's this angle right here, that's bigger. And then our last one is our equiangular triangle. Equiangular is actually the one where then they are all 3 congruent. So these are my 4 options when I'm asked to classify my triangle by angles. I have acute, I have right, obtuse, or equiangular. So when I look at this first problem, we want to classify this triangle. We're going to classify it in both ways. We want to classify it by sides and classify it by its angles. So first, let's look at its sides. We can see we have 2 tick marks here. We have 1 on each of these sides, but we have nothing on this third one. This third one's just no tick marks at all. So my tick marks mean that they're of equal length. So if I have 2 sides that are equal length, so if you go back, then 2 sides is our isosceles. So here we have isosceles triangle. And then this one actually asks you to measure the angles. So if you go in your book, you can actually use a protractor and you can measure it. Since I'm not going to get a protractor out right now, to measure this, here I'm going to have a 55-degree angle. This one's a 55-degree angle. And then up here you would get about 70 degrees. So I have 2 angles that are the same, but ultimately when we're looking at angles, we're looking for, are they all less than 90? Do we have one that's equal to 90, or do we have a greater than 90? Or are they all the same? They're not all the same, only 2 of them are, so it's not equiangular. But they are all less than 90 degrees, so that means this is going to be an acute triangle. So it's isosceles and it's acute. So when we look at triangles, we have what we call the interior angles, which are just the angles inside here in the red. And then we have what we call exterior angles. Exterior angles are the angles that make a linear pair with our interior. Okay, so remember, linear pairs are 180 degrees. They're on the same exact line. So as you can see here, I would have my interior angle of B. Well, with this exterior angle, this whole degree measure is 180 degrees. It's a linear pair, it's on a line. So when we first look at interior angles, this is something that may be familiar to you from before, but interior angles of a triangle, no matter what triangle we have, if we have an acute triangle, we have a scalene triangle, isosceles, equiangular, no matter what triangle we have, the interior angles are always going to equal 180 degrees. So that's this angle of A, this angle over here of B, and this angle of C. They are all interior. If I add them up together, they always equal 180. Exactly. Then I have my exterior angle theorem, which just tells me that when I have an exterior angle, so in this case angle 1, the 2 opposite angles from the interior angle that it's a linear pair with, these two opposite angles, are always going to add up to be equal to that angle of 1. They're always going to be equal length. Because if you think about it, this angle of A, this interior angle of A, this interior angle of B, and this interior angle of C, they all add up to be 180. Well, this C plus this exterior adds up to be 180. So it's just basically they equal the same thing. And so if you were to look at the proof, then you would be able to see how it actually works. So we're going to go ahead and use this theorem in example 3. So here I have my exterior angle of K. It's JKM. They want us to find that measure. So since it's an exterior, I know it's equal to the two opposite angles added together. So if I add my opposites, I have 70 plus x equals that exterior angle of 2x minus 5. And then all I have to do is solve for x, and then I'll have to substitute back in. So if I solve, I'm going to go ahead and move my x to the right so it stays positive. Then I need to get my x by itself, so I'm going to add 5. So I get x is equal to 75. Then I have to substitute it back in order to actually find the measure of JKM. So when I substitute, I have 2 times 75 minus 5. 2 times 75 is going to give me 150 minus 5 gives me 145. So that would be my answer. So in this last example, we're told that the red triangle is a right triangle. It says the measure of one acute angle is twice the measure of the other, and find the measure of each angle. So in my picture, okay, and I'm just going to redraw this triangle. I know it's a right triangle, so I know I have my 90 degrees there. Then I'm told that the measure of one angle is twice the measure of the other. So I'm going to go ahead and give one angle a variable. I'm going to call it x. And then I know the other angle is 2 times that measure. So I'm going to have 2 times x. Thanks back to our triangle sum theorem, I know all angles in a triangle equal 180 degrees. So I'm going to go ahead and write that out. So I have x plus 2x plus this right angle here of 90 is equal to 180. Now all I have to do is solve for x. So when I solve, I'm going to first subtract this 90 over, and I'm going to go ahead and combine these terms. Okay, I'm going to do it in one step. So I have 3x is equal to 180 minus 90 gives me 90. Then I want to solve for x to get it by itself, so I'm going to divide by 3 on both sides. So when I divide by 3, I get x is equal to 30. So when I substitute in, I have one angle is 30 degrees. And then when I substitute into the second one, I have 2 times 30. So that means my other angle is going to be 60. It told me to find the measure of each angle, so that's what we did. We're going to go ahead and move on to 5.2, so congruent polygons. We're still primarily going to be talking about triangles here. Remember, a triangle is a polygon, it's just it's only a 3-sided. And so we'll be looking at some more theorems on this. So this slide, it has a lot of information, and you can find this in your book. It's in 5.2. Basically what we're looking at, we've already looked at geometric figures and being able to transform them. We've looked at what they call rigid motion. Rigid motion is just the ones where we didn't change the size of it. Okay, we kept the shape congruent. So those were our translations. That's our reflection. All of those things are rotation. Those 3 are ones that are rigid. Okay, whenever we do them, they're still exactly the same shape. They've just been changed a little bit. We just turned them or we flipped them. We did not change their size. So when we look at corresponding parts, if I have a figure that's been changed by a rigid motion, it's just been changed in one of these forms, then I can be able to identify its corresponding parts, and so I can still be able to make my congruent portions. Okay, I have corresponding sides, I'll have corresponding angles, and those corresponding sides and angles are going to be congruent to each other. So basically in this picture, we have DEF is the image of ABC. So ABC was our pre-image, and it was transformed into DEF by some sort of rigid motions. Okay, it looks like maybe it was possibly rotated, but it was also, or maybe it was just flipped. It was flipped across a certain line, or reflected across that line. So even though we reflected it, those corresponding portions, A and D, and then we have B and E, and we have C to F, they're still going to be congruent. So our angles, specifically, angle A is congruent with angle D, angle B congruent with angle E, so on and so forth. But then also our sides. And so you can see here the angle measures have been marked, the sides have been marked because they are still congruent. They are corresponding parts of those triangles, and that since that triangle is exactly the same size, the same shape, then those corresponding parts are going to be congruent with each other. So the biggest thing to note from this, as we look into it further, is whenever you write them, it's going to be very important you put corresponding portions in the same position. Okay, so in this example, since A and D are corresponding with each other, they're the same angle, they're the same exact point on that triangle, I always want to put them in the same position. So if I were to write triangle ABC is congruent with triangle, and I want to list this other triangle, I need to make sure they're in the same exact position. Since A is in this first position, D would need to be in that first position. Okay, because they were the same. There are red little angles here. Okay, then my next one, B is in the second position. It's the blue one. Then E would need to be in that second position. Then my third one of C, it's in that third position. And so that would mean F needs to be in that third position. Okay, my corresponding parts are listed in the same exact order. Even if I flip them around, say I decided I wrote it down the first time as CAB, then I would need to write them in the same order as that. So since C is first, that means F has to be first on this other side. Since A is second, that means D has to be second. Since B is last, that means E has to be last. Okay, my corresponding parts are in the same exact position. So that's all we're doing in this first example. We want to write a congruent statement for this triangle. So we need to put them in the same order. We need to put our corresponding parts together. So when we look at this picture, if I look at angle L is going to be congruent with the angle that has the same exact marks inside of it. So here it has one line. And so we would need the angle in this other triangle that only has one line. So that would be angle R. Then I would keep going. So angle J is congruent with angle one that has two marks. So that's angle T in this case. Then my last one, angle K, is congruent with one that has three. So that's angle S. Then I do this for sides as well. So whatever side I decide to start with, if I decide to start with L and K, that segment is going to be congruent with a segment that also has two lines on it. So when I look at my other triangle, I identify my two lines and my points that are off that same side. So that would be segment SR. Then I would want to do, I have J and K. That segment's going to be congruent with one that has this one mark. So it's going to be T and S. And then I have the last one of J and L. And so that's going to be T and R. So we've identified all the parts that are congruent with each other. Now we need to actually write the congruent statement for the triangles. So that means we have to write our triangle symbols. And we're going to have a congruent sign. But we have to list them in the same order. So if I decide to list this first one as LKJ, then I need to make sure they correspond with each other on the other side. The easiest way to do this is just by your angles. Find your angles that are congruent. So I start off with L. L has one line. Up here we said L is congruent with R. So that means I'm going to start with R. So K is my second one. K I said was with S. So S needs to be my second one. J is my last letter. I said it's congruent with T. So T has to be my last one. So my congruent statement is that triangle LKJ is congruent with triangle RST. So in this statement, we actually have quadrilaterals in example 2. So notice the statement that DEFG is congruent with SPQR. Okay, so if they made that congruent statement, that means they're going to be listed in the same order that they are congruent in. So first off, I can go ahead and just write those statements. So angle D, it's in the first position, so that means it's going to be congruent with angle S. Angle E is going to be congruent with angle P. Angle F is congruent with angle Q. And angle G is congruent with angle R. I can do the same thing trying to identify my sides that are congruent, just do them in pairs. So if I do DE, my first two of this one, I'm going to have DE is congruent with SP. I can go ahead and leave that there for a second and just look at the second set here. So I can do FG is congruent with QR. So here I did the first two, I did the last two. I can do the two in the middle. So EF is congruent with PQ. And then the last set I can actually make is doing the last two, the two outside ones. So here I have D and G is congruent with I have S and R on the outside. So those would be my congruent segments. So now that we've kind of looked at those, let's go ahead and look at our problem. We just need to find the value of x first for A. So if I notice x is on this angle here of Q, well, I know that Q is congruent with angle F. So that means the measure of angle Q, since it's congruent with angle F, is going to be equal to the measure of angle F. So now I can just substitute. So I have 6y plus x is equal to the measure of angle F, which is 68. But here I have two variables, and I can't solve when I have two variables. So let's look at what else we have. We also have this side length here that has an x in it. So QR, when I look at QR, I find that QR is congruent with FG. So if I just substitute those in, so I would have 2x minus 4 is equal to the length of FG, which is 12. And then I just solve for x. So if I add 4 to both sides, I get 2x is equal to 16. Divided by 2, I get x is equal to 8. So that's my first answer. X is equal to 8. Then I can go back to the problem I started to make earlier. Using that information, I'm just going to plug x in. So now I would have 6y plus 8 is equal to 68. To solve for y, I'm going to subtract this 8 away. So I get 6y is equal to 60. I divide by 6. So I get y is equal to 10. And then I'm done with that problem. So moving forward, triangles, we will end up being able to do proofs in triangles, just like we've done with other problems. In this first theorem here, all it's showing you is that these properties that we've had before, reflexive, symmetric, transitive, they also work with triangle congruence. Okay, they're the same exact property. Reflexive just means that it's the same thing as equal to itself. Okay, that's the same that we've done before. Symmetric is still, I can flip it around. My congruent signs, I can just change which side they're on my congruent sign, and it's still the same exact problem. It doesn't change anything. And then transitive is still our take out the middleman. If I cross out this middle portion here, I can combine the two outside to make one statement of my ABC is congruent with JKL. Okay, that's all this one's showing us. Same exact properties, just using it with triangles. Then we have third angles theorem. Third angles theorem just tells us that if I already know that two angles in my triangle are congruent, then I can automatically know that the third angle is congruent, right? Because think about this. If I know my two angles here, okay, if I know two angles in my triangle, I know angle A and I know angle B, well, we know all three angles in a triangle add up to be 180. So if I add them together, I would be able to find C no matter what. Same thing would happen in F. I would be able to find F by being able to add the other two, subtract it from 180. If I know, though, that the angles are the same in two triangles, then I automatically can know the third angle is going to be the same. Because if I solve for C here, and I solve for F here, and I know that originally those other two triangles, my B and E and my A and D, were exactly the same, then C and F, of course, if I solve them, it's going to give me the same exact answer. So we're actually going to use that here in this problem. This problem, we have two triangles. They're just intersecting, okay? Don't let a shape like this throw you off. If you want to, you can actually unseparate these triangles. So if I want to redraw this triangle out, I can draw my triangle of ACD. All I'm doing is pulling out this section, this whole triangle, to this portion. And so I know here A has one line and it's 45 degrees. Over here it has two lines, which is 30 degrees. Now I'm going to take out my other triangle. So I can take it out and it's going to just look just another triangle. It doesn't have to be drawn to scale, obviously. I'm just pulling it apart so you can see the two triangles. Don't let something complex like this, just because they intersect and they make this new point of N, don't let that throw you off. B has one line, and then C has two lines. So when I look at this picture, I can know that B is going to be 45 degrees because it has one line just like A. Okay? These angles are the same because they both have one line on the angle. They're telling me that they're congruent. Then I can also know D, or not D, I can know that D and C are the same because of the two lines. So I know C is 30 degrees, again, because I have two lines on each one, so they're obviously congruent. And so third angle theorem tells me that if I find the third angle in one triangle, it's going to be the same as the third angle in the other triangle. So BDC is what we're looking for, but we're actually going to solve for C over here. Just this angle of C right here. So I know that three angles in a triangle add up to be 180 degrees. So if I just look at this angle over here, then if I add them up, if I add my 45 and my 30, and I add this variable, say we call it X, then they're going to sum to be 180 degrees. Okay, three interior angles in a triangle add up to be 180. So if I do 45 plus 30 plus X equals 180, I can solve for it. So 45 plus 30 gives me 75 plus X equals 180. Subtract my 75. And so I get X is equal to 105. Third angle theorem tells me since this angle equals 105 degrees, it's the third angle in my first triangle, then since my other triangle has the same two angles, the third angle in it also has to be 105 degrees. So that means that the measure of angle BDC is equal to 105. And if I tried to solve for that, then it would look just like the work that we did over here. It's the same exact triangle angles, and so my third angle is going to be exactly the same.